All right, so now we need to start solving some higher order, say second, third, fourth order linear differential equations start to finish. In this case, we're going to look at a very specific type of linear equation that we're going to solve. So in this type, it's going to be homogeneous. So that means it's going to be equal to 0. It's going to be linear, so all the criteria we need for linear. And it's going to have constant coefficients. So all the coefficients that are supposed to be functions of x for a linear equation, they're only going to be constants. That's the best we're going to get. And we've seen this in a first order. We've seen a first order of the form generally y prime plus ay equals 0. We saw one, I believe the example we did was probably one of the first examples we did, and it was y prime plus 3y equals 0. And I mentioned to you, look at the answer that we get. And the answer happened to be this exponential function. And it was c e to the 3x. Okay? But if we just call it a for any constant, we see that we get an exponential solution is the whole point. And so for a first order linear homogeneous with constant coefficients, we get an exponential solution is the whole key. So then we go, well, if we increase the order to second, third, fourth order, but still keep it with constant coefficients and homogeneous, we should probably expect that exponential solutions should exist there as well. So let's make the assumption that they do. And so what we're going to do is we're going to look at a second order linear homogeneous differential equation with constant coefficients. And the constants will be a, b, and c. So a, b, and c are just going to be constants. And we're going to make the assumption that some exponential function, say y equals e to the mx, would satisfy this equation. Well, the idea, though, is if it satisfies that equation, if it's a solution to that equation, then when I plug it in here for y, and I plug the derivative, which would be m e to the mx in here, and the second derivative, which would be m squared e to the mx, is plugged in here, the left side should equal 0. So that's what we're going to do. What we're going to do is we're going to plug it in, and we're going to see what happens. And essentially what we're going to do is we're going to figure out, well, if this were in fact to solve the equation, m, which is some constant right now, okay, that m is just a constant, what would m have to be for this to work? And we use this trick a lot this semester, where we're going to look at solving a differential equation. We're going to make some assumption on what the solution should be, and we're going to go ahead and plug that in and see what happens. And by see what happens, I mean what would the criteria be for that to be a solution. And so when we plug it in, pretty simple. We plug this in for y prime, so we would get a times m squared e to the mx, plus b, we plug this in for y prime. Sorry, this was y double prime. We plug this in for y prime, which is m e to the mx. And then cy, y was e to the mx, and that should equal 0. And what you see is they all have an e to the mx in them, so if I factor that out, e to the mx, I get a m squared plus bm plus c equals 0. And that's what you're seeing here and then here. Okay. Now, a couple of things we know here. One, this is two pieces, two expressions multiplied together equal to 0. We can invoke the zero product property, which says one of these has to equal 0. Okay? Not both, just one. One of these two things, when you have two things multiplied together equal to 0, one of them has to equal 0. Well, e to the mx never equals 0. It's an exponential function. Exponential functions don't ever equal 0. So that's out, okay, for all x. So then that tells me that this has to equal 0. For e to the mx to satisfy this differential equation, this would have to equal 0 so that the left side could equal the right side, so that it could be a solution. Well, if I have to figure out what m's would make am squared plus bm plus c equal 0, that essentially amounts to solving this quadratic equation for m. And as long as I can find a solution to this quadratic equation for m, then e to the mx will satisfy the corresponding differential equation. And this equation is called your auxiliary equation. And so what we're going to do basically is we're going to solve differential equations by solving quadratic equations, which is really nice because quadratic equations are easy to solve, as long as you remember how to do that. Now, if you're in differential equations, you should know how to solve a quadratic equation. When you solve a quadratic equation, there are three things that can happen. First off, when you solve a quadratic equation, you always get two solutions. I know in algebra, sometimes they tell you you get at most two solutions, but that's if we're specifically talking about distinct real numbers. So when you're in basic algebra, you tend to ignore imaginary numbers. So then if we stick in just the real number sense, you're usually told that, oh, in a quadratic, you can get 0, 1, or 2 real solutions. And, well, that's just not completely true unless you ignore imaginary numbers. At this point in differential equations, we should not be doing that. We should be discussing a little bit more about complex or imaginary numbers, and complex numbers are built off of that. So anyway, there are two solutions, okay? When you solve a quadratic equation, there's always two solutions. And it's just a matter of what do those solutions look like. Well, there are three options for what those solutions can look like. One option is that both of those solutions are real and distinct, so they're different. So you get two solutions, M1 and M2. They're both real numbers, and they're both different real numbers. That would happen if the discriminant is greater than 0. The discriminant is the term inside the square root in your quadratic formula. So when you solve your am squared plus bm plus c equals 0, you could solve that using the quadratic formula for m, which would be minus b plus or minus the square root of b squared minus 4ac all over 2a. And this right here is what we call your discriminant. And what happens with that really dictates which one of these three scenarios you end up with. So the discriminant is positive, okay? So you get the square root of a positive number, you plus and minus it, and that's where you get your two real solutions, two distinct real solutions. Second possibility is M1 and M2 are real, but they're equal, okay? They're the same solution. We call that a repeated solution. And you could say, well, it's only one solution, but technically it's two solutions. They're just both exactly the same. And so that's when the discriminant equals 0. The discriminant equals 0, essentially taking the square root of 0, this whole square root drops off. So you're adding and subtracting 0. We ignore that. And our solution in that case, so in this case, your solution for m would be negative b over 2a. Okay? And that's a repeated solution. There's two of those. Third scenario is M1 and M2 are what we call complex conjugate solutions. Okay, and that happens when the discriminant is negative. The discriminant's negative, we then take the square root of a negative number, imaginary numbers have to come into play, and we get what we call complex conjugates, where M1 and M2 equal alpha plus I beta, and M2 is alpha minus I beta. Okay? Let's say beta. And alpha and beta are real, and I is your imaginary number. Together, this forms what we call a complex number, and they're complex conjugates because here you're adding alpha plus I beta, and here you're subtracting alpha minus I beta. Okay? So whenever you add and subtract the same two terms, we call that conjugate. So these are complex conjugates. And so that happens again when your discriminant is negative. So those are the three scenarios. And so what we need to do is look at these three scenarios a little bit closer so that we can then see how the solutions to the differential equation develop based off of these three scenarios. But when you solve a quadratic equation, there definitely are solutions. There are always two solutions. So therefore, we should always get two solutions to the differential equation. First scenario. Under the assumption that the auxiliary equation has two unequal real roots, M1 and M2. So this is the first scenario. M1 and M2 are unequal, distinct, real roots. Okay? So the idea here would be then, that tells us that y equals M1, e to the M1x is one solution, and e to the M2x is another solution. And what we learned was that we can then form a fundamental set of our solutions because these are linearly independent, which we saw in the beginning of the chapter, that any solution of this form would be linearly independent solutions, and we can form the general solution by saying C1y1 plus C2y2, or C1 e to the m1x plus C2 e to the m2x. And so here's an example of something like this happening. So here's a differential equation. Solve 5y double prime minus 4y prime minus 12y equals 0. Notice, this is linear, homogeneous, with constant coefficients. So what we're going to first do is we're going to solve our auxiliary equation, which would be 5m squared minus 4m minus 12 equals 0. So we solve that quadratic equation any way you want. It's a quadratic equation. You can use quadratic formula. We can use factoring if it's possible. We can use completing the square, extracting the roots if it's possible. You learned 4 different ways to solve quadratic equations back in algebra. Pick one that works for you and do it. So in this case, if I was going to solve this quadratic equation, I would, let's try and factor it. 5m, m, what are we going to get here? 4, let's go 2 and 2, okay? That's not going to work. What am I doing? So we would put, what is this, a 2 and a 6, so we would get a negative 4, so let's go negative, positive. There we go. So we would get m equals negative 6/5 and m equals 2. So notice that we get 2 distinct real solutions to the auxiliary equation. So that tells me that y equals e to the negative 6/5 x is one solution to the differential equation, and y equals e to the 2x is another solution to the differential equation. So therefore, the general solution is y equals c1 e to the negative 6/5 x plus c2 e to the 2x. That whole thing will solve the differential equation. Again, it can't get much easier than that. We're using quadratic equation solutions to solve a differential equation. It's pretty nice. Case 2, the repeated reals. So m1 equals m2. Okay? So that tells us that y equals e to the m1x is one solution to the differential equation. But e to the m2x is not a different solution. So we only really get one solution here. We want to find a second solution to the differential equation. Remember, m1 would be negative b over 2a because the discriminant would be 0. So then what we want to do is we want to find a second solution. Well, guess what? We learned previously, if you have one solution to a differential equation, how you can use that to obtain a second solution. So we have a formula for that. And the formula for that was that y2 should equal y1 times the integral of e to the negative p over y1 squared dx. Okay? And so if you look at this differential equation, ay double prime plus by prime plus c equals 0, and you look at what p would be, well, p would be b over a, because we'd have to put this in standard form to find p. And so if we look at this integral here, yes, this should be the integral of p dx, what you're going to get here is e to the negative integral of b over a dx which is going to give me e to the negative b over ax. Okay, so that's this first part, and you see that here. And y1 is e to the m1x. So we have e to the m1x, e to the m1x, but that has to be squared. So right here, this is set up to find our second solution. Then, remember, m1 is negative b over 2a. Okay, negative b over 2a. So, if you think of that as m1 equals negative b over 2a, if I multiply the 2 over here, then 2m1 equals negative b over a. Well, if I replace this negative b over a with 2m1, and I square this, which means I have to have a power to a power, so I multiply, that's 2m1x, which means these two are going to cancel each other out. So I have e to the m1x times the integral of, this turns out to just be 1 dx. Well, the integral of 1 dx is just x. So that tells me my second solution should be x e to the m1x. And that's always going to occur if we have that repeated solution, because I didn't say what m1 is other than it's a real repeated solution. So this is what the second solution will look like. So then we put that together and say, well, then the general solution should be the first solution plus the second solution. So c1 e to the m1x plus c2x e to the m1x should be how we solve a differential equation if we have repeated real roots. So here's an example. So first we'll create our auxiliary equation. Notice linear, homogeneous, constant coefficients. Okay? So our auxiliary equation would be 4m squared plus 4m plus 1 equals 0. We solve this quadratic equation. Again, we should be able to factor this. If not, we'll use quadratic formula, but I think this is factorable. 2m plus 1, 2m plus 1. Okay. That'll give me 4m squared, that'll give me 1, then 2m and 2m gives me the 4m. So that's our quadratic. Notice the factors are the same, so what do we get? We get a repeated real solution, that m equals negative a half. And that's going to occur twice, right? 2 times. So repeated real. Repeated real states that the solution to the differential equation is y equals c1 e to the negative 1/2 x, because that was the first solution, plus c2 x e to the negative 1/2 x. There's your second solution. And therefore, this is your general solution to the differential equation. Again, pretty easy, as long as you know what to do when you get to this scenario. Distinct reals, repeated reals, and then we have our third scenario. Now, the third case is a little bit more involved until we get to find out what the final answer should look like. And so it's only more involved because you probably have a little less experience with complex numbers than you do with real numbers. Obviously, you've been dealing with real numbers much longer. And so if we look at the complex roots and say m1 and m2 are complex conjugates. So m1 is alpha plus I beta, and m2 is alpha minus I beta. Again, where alpha and beta are real, and I is the imaginary number such that I squared equals negative 1. Okay? Or you could say I equals the square root of negative 1. Now, this is really not any different than in case 1 where we had 2 different real numbers, right? We have 2 distinct real numbers. Here we have 2 distinct complex numbers. And so we could say, well, the general solution is c1 e to the m1, which is alpha plus I beta x, plus c2 e to the alpha minus I beta x, which is m2. And we could say, okay, there's our solution. The problem is that solution is based off of complex functions instead of real functions. Now, this right here would be a complex function. And we would prefer to have our solution to have real functions in it. we're solving differential equations. We've been dealing with real functions all throughout calculus, okay? You have not done complex calculus yet. So we're not there yet. And then you could take a whole course on complex variables, which would really basically help you learn complex calculus. Typically, you do that in your junior year. But anyway, we would like to find real functions. So we can. What we need to do is use a couple of things that come up in complex variables course. One specifically is this Euler's formula. So Euler's formula sits right here. And it says, if you have e to the I theta, where I is your imaginary number and theta is a real number, okay? You could rewrite that as cosine theta plus I sine theta. Euler's formula. Not going to get into where that comes from or why it is what it is. You could learn that in your complex variables course. Okay? But yeah, theta is a real number. All right, from that, what we're going to see is that if I had e to the I beta x, I could write this as cosine beta x plus I sine beta x, where beta x is in place of the theta. And if I had e to the minus I beta x, I could write that as cosine beta x minus I sine beta x. And that's where where theta would be negative beta x. And in that case, we're also using the idea that sine and cosine are even and odd functions, respectively. Then what we could do is if we were having to add e to the I beta x plus e to the minus I beta x, so we're adding these two things together, you would see that the signs would cancel each other out, and we would just get 2 cosine beta x. If we had to subtract those things, then what would happen is the cosines would cancel, and we would end up with 2I sine beta x. All right. So now we're all kind of set to go. These are the things we need to move forward. So let's look at this original solution here. And let's say that C1 and C2 are both equal to 1. If they are both equal to 1, because remember, they're just random constants, if we let them both equal 1, we would get this solution. Okay? We'd say, okay, here's the solution. Call this y1. And if we let C1 and C2 equal 1 and negative 1 respectively, we would get this solution. Okay. Then what we can do is we can say, all right, well, if we were to look at y1 a little bit closer and rewrite it, well, e to the alpha plus I beta x, and the same thing would go for e to the minus alpha minus I beta x, can be written as e to the alpha times e to the I beta x. Because I'm adding in the exponent, I can write it as multiplication of bases, which would then allow me to factor out an e to the alpha x. Sorry, this is all in parentheses, so this would be alpha x. And I would get e to the I beta x plus e to the minus I beta x. Well, we already said that this e to the I beta x plus e to the minus I beta x would be 2 cosine beta x. So in essence, we could take y1 here and actually rewrite it this way. And the same thing could go for y2. I could factor out an e to the alpha x, leaving me with e to the I beta x minus e to the minus I beta x. But we already said that that piece is equal to 2I sine beta x. So then y2 could be rewritten like this. We're almost there. All right. Well, remember, the general solution should be c1y1 plus c2y2. If we use these new versions of y1 and y2 that we've come up with, what we can do here is we can say, well, we would have c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. Now the question is, what happened there? This was y1. Where did the 2 go? Because I don't see the 2 here in y1. Well, the 2 got embedded inside this c1. 2 is a constant. c1 is a constant. So if I wrote this as 2c1 e to the alpha x cosine beta x, we could. But since this is all one big constant, we're just going to call that whole thing c1. And then everyone goes, well, what about y2? y2 look like this. And so it should be, this right here should be c2 2I e to the alpha x sine beta x. However, same as over here, the 2 is a constant, But I is also a constant. It's an imaginary constant, but I is a constant. So I could lump all this in together and call it C2. And so that's what you see here. Now, what you look at is there are no complex components to this solution. So all I do is factor out an e to the alpha x, and here I am. So, getting rid of all this, the big picture here at the end is that your solution for the general form should be in the form of e to the alpha x times c1 cosine beta x plus c2 sine beta x. And that's really the important part, where alpha and beta come all the way back to here when we had the complex conjugate solutions to our quadratic equation. But this is what the final result should be. You don't have to run through all this every single time. As long as you know what the final result should look like as the solution, the general solution to the differential equation in this scenario, that's the big one. So we look at an example of this. So here is your linear, constant coefficient, homogeneous differential equation. We create our auxiliary equation, which would be m squared plus m plus 1 equals 0. And we're going to solve this one. The only way to solve this one would be using the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So we get negative 1 plus or minus the square root of negative 3 all over 2. I could also write this as negative 1 over 2 plus or minus the square root of negative 3 would be the square root of 3i all over 2. Basically split this up into two fractions. And here you see your alpha plus or minus I beta, where alpha is negative 1/2 and beta is square root of 3 over 2. Okay. Once you have that, then we could say the general solution, to the differential equation is y equals e to the alpha x, so negative 1/2 x, times c1 cosine beta, square root of 3 over 2x, plus c2 sine beta, which is square root of 3 over 2x. And that's it. So as long as you know what to do with your alphas and your betas, you're good. A lot of students ask, what about beta? Is beta negative square root of 3 over 2 or positive square root of 3 over 2? No, beta is just square root of 3 over 2, so it is positive in essence. You add and subtract beta, so this is the plus and minus here, so beta is the square root of 3 over 2. So it's always the positive value there for beta. Here's another example. Right, in this case, we're solving the general linear here, where k is a constant. So y double prime plus k squared y equals 0. In which case we would say, oh, well, this is linear, homogeneous with constant coefficients since k is a constant. My auxiliary equation would be m squared plus k squared equals 0. There is no m because there is no y prime. That's a mistake a lot of people would make here, is they would say k squared m, but no, k squared is just the constant, because this is y to the first, not y prime. And so we solve this one. Well, we could solve this pretty easily. We could say m squared equals negative k squared. So m equals plus or minus the square root of negative k squared, giving me plus or minus the square root of k squared, which would be k, and the square root of the negative 1 would be I. So if we look at this as alpha plus or minus I beta, alpha would be 0 and beta would be k. Therefore, our general solution to the differential equation would be e to the alpha x, so e to the 0x, times c1 cosine kx, because that would be beta x, plus c2 sine kx. Well, notice e to the 0x is just 1 because that's e to the 0, so technically we don't have to write that. So we really could say the solution is c1 cosine kx plus c2 sine kx. Now that we've seen what happens with second order linear differential equations that are homogeneous with constant coefficients, we want to move up to higher order ones, so third order, fourth order, fifth order. Well, essentially the same thing keeps happening. Okay? If we have constant coefficients and we have a homogeneous linear equation, the first order had an exponential solution. The second order has two exponential solutions, essentially. The third order, you should expect exponential solutions to also work. Fourth order, fifth order, sixth order, we shouldn't expect this pattern to cease to work. And so what happens is it does. When we look at having these exponential functions solve these higher order ones, essentially what it amounts to is to solve a nth degree polynomial auxiliary equation. So if we have an nth order differential equation with constant coefficients, okay, and it's homogeneous, we can amount that to an auxiliary equation that turns into be an nth degree polynomial equation. So something like this would be our polynomial equation that we need to solve. And as long as we can find what m solves that auxiliary equation, then e to the mx should solve the differential equation. Okay? Now the only problem here is how do we, well, a couple problems. One, how do we solve these polynomial equations? Well, you should know how to do this. We've done this in algebra. The primary way you do it once you pass your quadratic equations is factoring, right? Factoring is the basic way you solve these ones. And then we say, okay, well, what about the solutions? What do they look like? Well, they still fall into three categories. They're either distinct real solutions, they're repeated real solutions, or they're complex conjugates. The only difference is there are more of them. So if you were to solve a third order polynomial equation, you always get three solutions. A fourth order equation, you always get four solutions. They're just going to be a combination of possibly distinct reals, repeated reals, or complex conjugates. Remembering that complex conjugates always come in pairs. So if you have three solutions, say you have a cubic equation, third order equation, and you know you're going to get three solutions, and two of those solutions are complex conjugates because they come in pairs, the third solution's only option is to be a real solution, right? But once you decide that, okay, then how do we go about it? Well, what if we have our distinct real solutions? If all roots are distinct real solutions, m1 doesn't equal m2, doesn't equal m3, doesn't equal mn, whatever, however many we have, then our general solution should just be c1 e to the m1x plus c2 e to the m2x plus cn up to the e to the mnx. That's it. Just keep writing them, just like we did. Just there's more of them. What if we have repeated real solutions? So m1 has multiplicity k. Multiplicity k means the number of times it's repeated. So it's repeated twice, 3 times, 4 times. How many times is it repeated? Well, the number of times it's repeated will just affect the number of solutions we have. So in this case, let's say m1 is multiplicity k. So that tells us that e to the m1x is one solution. And the second solution, we already know, should be x e to the m1x. And then the third solution should be x squared e to the m1x. And then x cubed e to the m1x, all the way up to x to the k minus 1 e to the m1x. So you just keep dumping an extra x every time it's repeated. 2, 3, 4 times. You have to write all of them out. Every time adding an extra x onto the front here. So x to the first, x to the second, x to the third, all the way up to 1 less than whatever the multiplicity is. And then finally, your complex conjugates, same as before. They come in pairs, and so you should have your e to the alpha x plus c1 cosine beta x plus c2 sine beta x. Okay? So when we look at this scenario, if we had, say, a fifth degree equation, there should be 5 solutions altogether. If there are 5 solutions, we could say we have 3 distinct and 2 complex. We could say we have 1 distinct real, a repeated real, so there's 2 of them there, and then a complex conjugate pair that would add up to 5 altogether. And we could do all sorts of combinations, but they still fall into the 3 groups: distinct reals, repeated reals, or complex conjugates. Heck, we could have 5 repeated solutions for the 5th degree, so they're all repeated solutions. We could have 2 pairs of complex conjugates and then 1 distinct real. Again, any way to get to 5, remembering though that the complex conjugates come in pairs. So here is an example. Notice this is a 3rd order homogeneous linear differential equation with constant coefficients only. Okay, 1, 3, 2, 6. Those are all constants. So it has the exact form that we need. It's very specific. So our auxiliary equation would be m cubed plus 3m squared plus 2m plus 6 equals 0. And we need to go ahead and solve that. And so since it's a cubic polynomial, the best way typically to solve these is to factor. So use all your skills of factoring you've learned along the way. In this case, this is a pretty easy one to factor by grouping. So pull out an m squared out of the first 2 terms, you get m plus 3. Pull out a 2, you get an m plus 3. So then you get m plus 3 times m squared plus 2. So this would tell me that m equals -3, and this one right here would tell me that m equals plus or minus square root of 2i. Okay? Again, because you would get m squared equals -2, and therefore m equals plus or minus the square root of -2, and that gives me plus or minus square root of 2i. So what do we have here? We have a real solution, and we have complex pair, but we have 3 altogether. Here, alpha is 0 and beta is root 2. And so if we're going to write the general solution, it should be c1 e to the -3x, that's the real solution, plus e to the 0x times c2 cosine square root of 2x plus c3 sine square root of 2x for a complex pair. We probably wouldn't write this e to the 0x in there. So if I was to clean this up, c1 e to the -3x plus c2 cosine of square root of 2x, there should be an x here, plus c3 sine square root of 2x. There is our solution to our differential equation. And you notice we basically have these 3 functions here that solve the differential equation. All together gives us a general solution. Here's another one. In this case, we have a 4th order differential equation, but it is still homogeneous and it still has constant coefficients. In this case, 1, 8, 16. And so if we create the auxiliary equation for this, we would have m to the 4th plus 8m squared plus 16 equals 0. There's no 3rd derivative or 1st derivative, so there's no m cubed or m to the 1st. So we're going to solve this again. Factoring is your best way to do it. This one's a pretty easy one to factor also. The problem is these higher order polynomials aren't always easy to factor, and that's going to be probably the thing you struggle with the most here. And so it would be m squared plus 4, and m squared plus 4 would give us the solution to this. And so that's going to give us what? M squared plus 4 equals 0, but it's repeated because there's 2 of them. So what do we have here? We have repeated complex conjugates. All right, we'll deal with that. But what is the solution first off? This would be m squared equals -2, so m equals plus or minus, -4, so m equals plus or minus 2i. Okay? So in this case, you got alpha to be 0 and beta to be 2 again. And so the idea here is that we would have a repeated solution though, right? This is repeated. So not only do we have a complex conjugate pair, but we have a repeated complex conjugate pair. So we have kind of a combination of things here. So we would say the first solution would be e to the alpha x, which is 0. So we're getting to the point here where we know we're not going to write that. So just c1 cosine 2x plus c2 sine 2x. So that takes care of the first conjugate pair. But then that's repeated. So what are we going to do? Well, what we're going to do is we're going to do the same thing we did with repeated solutions when they were real. We'll throw an extra x out in front, and then we'll write the solution again. So C3, we should say here, 3 cosine 2x plus C4 sine 2x. And so there's our solution to the differential equation. So if it's a repeated complex conjugate, treat it like it's the repeated real. We throw an extra x. If it's repeated again, we'd have another one with an x squared in front of it, etc. So once you know the first three scenarios, we just keep extrapolating that out further and further for these higher order ones. All right, we got one more. Here we got a third order. Again, constant coefficients, linear, homogeneous. The hard part here is the factoring, right? Factoring isn't always simple, and so you might need to go back and review some of your factoring techniques you learned along the way. First off, the auxiliary. 3m cubed plus 5m squared plus 10m minus 4 equals 0. Right, so we want to factor this. Grouping's not going to work. We can't factor out a common factor. So you got to think about this. Well, one way you learned how to factor was through synthetic division. And so I can sit here and say, okay, let's do synthetic division. 3, 5, 10, negative 4. If this does not look familiar to you, you're going to need to go back and review this. You can go back to my website with some pre-calc videos, and I do synthetic division thoroughly in there. You can go back and look at that. And so what we need to do is figure out what can we divide by that would give us a remainder of 0. Okay, and that'll help us find the factor. And one way to do that is what's called the rational zero test, in which you take factors of negative 4 and divide it by factors of 3. And so factors of 4 would be 1, 2, and 4. 3 would be 1 and 3. So we take 1, 2, or 4, and we divide that by 1 or 3. So you could have 1 divided by 1, 2 divided by 1, 4 divided by 1, or 1 divided by 3, 2 divided by 3, 4 divided by 3. And those are all the things that could possibly work here. And so to make this go faster, I know that 1/3 is going to work, so I'm just going to use that. What you do is you bring down the 3. And it's really just a trial and error thing is where you would come up with a 1/3. So 1/3 times 3, those multiply, you put it here, that would give you a 1. You add straight down, gives you a 6. Do it again, 1/3 times 6 gives you 2. Add straight down, you get a 12. One more time, you get 4. Negative 4 plus 4 gives you 0, which is what we wanted. We want that to be 0. Tell us the remainder is 0. So that means that m minus 1/3 is one of the factors, because we divided this polynomial by m minus 1/3 and ended up remainder 0. And the other factor is the quotient, which is sitting right here, which would be 3m squared plus 6m plus 12 equals 0. Or sorry, 12 should be parenthesis here, and that equals 0. And so now we factored it, right? We started factoring it, and we can factor it even more in that we could factor a 3 out of here. So we have m minus 1/3 times 3 times m squared plus 2m plus 4. And we get, all right, well, this is a quadratic. That's not actually factorable, so we could use the quadratic formula to solve that piece. This one we know would be m equals 1/3. So this one's going to give us m equals negative 1 plus or minus square root of 3i when we use the quadratic formula. In which case, what do we have? We have a real solution, and we have a complex conjugate pair. We got our alpha, we got our beta. So then our differential equation solution should be c1 e to the 1/3 x plus e to the negative 1x times c2 cosine square root of 3x plus c3 sine square root of 3x. And it's all a matter of being able to do the algebra, right? And if you can do this, you're good. If you have to review factoring and synthetic division and all that, go for it. That's probably where you're going to, get tripped up the most because it might have been a while since you've seen it, but you should be able to handle it. But this is what we want, the solution to the differential equation.